started here. This is the ventilator preliminary design review. Welcome everyone. Thank you for joining us on your Saturday. The purpose of this meeting is to present end-to-end hardware design. I think we've been all working on various parts of the ventilator, but to try to go through it from top to bottom and get everyone's questions answered is a really good thing to do. And also to solicit feedback and get everyone's questions and concerns on the design before we go further down this design path. And I want to be clear, the goal is not to solve all the design questions and issues in this meeting. That's probably not possible, but to get everyone looking at the design and to get everyone thinking about the design as a whole. Just a quick point to request for a big Zoom meeting. This is, I've not run a big Zoom meeting before, so still trying to get the lay of the land, but it seems like if you can mute your mic when you're not speaking, that will help. And if I do say something that's incorrect, I'm going to be representing quite a few people's work here. So if something is wrong, just unmute and stop me right away, like immediately in the presentation. But otherwise, if you have questions or issues, we're going to be discussing those in the hardware PDR Slack channel. And we'll cover as many of them as we can at the end, and then continue the conversation on the Slack channel after the meeting is over, because I imagine a lot of these discussions will be ongoing. Okay, so this picture here, this is where we're at right now. This is our hardware prototype sitting on my dinner table right now. But we're at a place where every major component of the ventilator is represented in the prototype, with the exception of the mixing chamber for oxygen and the humidifier. But we have at least working models, if not the things that we actually want. Working models for the inlet and outlet flow sensors, pressure sensor, outlet orifice, outlet solenoid, the blower and drive electronics, and the Arduino controller, and then it's all hooked up to a test lung over here. And the objective where we're trying to get to here. So this is our 3D rendering that Elizabeth made for us. And a lot of what this design meeting is about is to bridge the vision between this and this. So our overall design objectives, what we're trying to do is design and build a ventilator that provides the level of care required for effectively treating COVID-19 patients. So there's a lot of projects out there that aim to inflate a bag, that aims to make a test lung move, and we're trying to be a bit more focused with that, with all our doctors, with all our reviews of the papers, to try and make sure that we really have the right modes and controls specifically for the type of treatment that ARDS COVID-19 patients will need to make it all the way from disease to recovery. So a lot of the other designs out there are bridge designs. They're intended to help keep a patient alive when they enter the hospital, but eventually they still need to they will most likely end up being transferred to what is considered a full-featured ventilator. And so what we want to do is build a ventilator that has those features so that we don't end up just taking up another ventilator eventually, right? And so the design must also provide the right feedback for the caregivers to be able to set the course of treatment to bring people all the way back to recovery. The other objective, the design has to be sourceable, and it has to be buildable in a repeatable fashion. And we're also trying to keep the unit material cost down to under 500 or some number around there. But the idea is to try and make something that's more buildable and more affordable for the countries that we're trying to serve. And then finally, another design objective is to limit the waste of consumables, which are limited supply items. So things like HEPA filters and the hospital's O2 supply. So we have a specific hardware requirements document. So the link is here in the slide, and these slides will be linked to and made available on the Slack channel. Here we're keeping track of every single requirement, every single specification that we need to meet. But just an overview, I'll give here on the slide. One of the modes we have two basic modes that we are trying to that we're trying to hit. This is the pressure regulated volume controlled mode. And this is intended for patients that are unable to breathe on their own and are usually fully sedated and intubated. So this one is fully autonomous. Every breath is controlled by the machine. It has a closed loop control of pressure, the patient pressure, and it tracks a machine initiated breathing cycle. So the machine has a profile that is intended for the patient, and it repeats that profile every number of seconds as long as the machine stays in that mode, regardless of the patient condition. And the machine will try to hit a target tidal volume. So this is something that the doctor will set, and it can vary those parameters to try and meet that tidal volume. And if it doesn't, it will sound an alarm. The other mode of operation that we're trying to provide is called assist control ventilation. And so this is for a patient that is either just starting on the ventilator or is now recovering from the disease and is being weaned off of the ventilator. So what that means is we basically have a dial where we can adjust the sensitivity of the machine to the patient's own breathing effort. And so the machine will synchronize to the patient breath. The patient will initiate the breath, and the machine will follow that patient's effort and provide support in order to bring the patient back to full recovery. I think we have someone with a hot mic there. Thank you. We want to permit user control of these mode parameters. So for PRVC, we have the peak inspiratory pressure, or PIP, the positive end expiratory pressure, or PEEP, the IE ratio, which is inspiratory-expiratory ratio. So that's the time ratio between how much time is spent inhaling versus exhaling, the respiration rate in breaths per minute, and the target tidal ventilation in milliliters. In the assist control mode, we basically have all of the same parameters for PRVC with the addition of the assist sensitivity. And that is, again, a dial that we can set of how much the machine, how much support the machine provides the patient, so that the patient can gradually be moved back to breathing completely on their own. And then the machine must display feedback to the therapist of the patient lung condition. So in most cases, this is a time history of the pressure and volume of the patient's lungs. And from that, the doctor can assess how the patient is doing and make adjustments based on that. And then finally, the system must sound alarms and display alerts based on either failures in the machine or changes to the patient's condition. And all these specific, all of these requirements are broken down into specific measurable tasks, basically, in the doc that is linked here at the top of the slide.
Hey, Edwin, that was a great overview. I have a few questions just because they've come up a lot in the chat. So for the AC, the assist controlled ventilation, you don't have tidal volume listed here. And generally AC has a tidal volume control as well. Can you explain why we're not doing that?
I think it's just missing there, so I'll add it in. There's no reason not to provide tidal volume control in assist. It really should be all of the parameters of PRVC with the addition of an assist sensitivity.
Yeah.
Thanks, Daniel.
Mm-hmm.
System block diagram. So this is the high-level view of how all the pieces in the system are intended to interact. Something I should mention before, this is the preliminary design review, so some of this stuff is still up in the air, but this is sort of a concept of how we intend this thing to work, how we see it working, and this will be adjusted as we continue the design. At the top, we have the display and the user interface computer. So this is kind of like a level diagram here. Present to the user is this user interface computer, which handles the graphical display of the sensor data and also allows the user to set the cycle parameters for the operation of the ventilator. So this data is passed back and forth to a cycle controller. So this is the real-time computer, the one that handles the real-time control of the system, of the actual hardware. This passes control signals down to the interface and drive electronics, which is a circuit board that contains our sensors and our interfaces between the computers and the electronics, and it passes back sensor readings to the cycle controller, which then passes those back up to the user interface. Then you have the actual hardware of the ventilator. This is the pneumatic circuit, includes blowers, motors, hoses, valves. This passes sensor data in the form of sensing tubes. So we have sensors are connected to the individual pneumatic components using tubes that carry the pressure. And then the main actuator of the system, or the main two actuators of the system, are the blower and the valve. And so we have a blower that can be throttled electronically, which is our pressure source, and a valve, which is our exhaust control. And then it's the interface to the patient is air and O2 on one side and the exhaled air on the other side. So as mentioned before in the diagram, oh, and also one more thing here in the system block diagram, a way to think about this is the time scales of each of these. So generally, we have an increasing time scale as we go up the chain. So the patient is immediate, like this is physics, happens immediately. The pneumatic circuit has some delay in responding to that. The electronics then operate on top of that. The cycle controller is operating at like 100 times a second. You know, it's making changes to the throttle on the like 1/10 or 1/100th of a second cycle. And then the display interface operates on the user cycle, which is from breath to breath. So, you know, every 10 seconds or so. And then between times that the user will change settings, which will be on the order of minutes, you know, tens of minutes.
Hey, Edwin, quick question. Yeah. Is there also going to be a port for administering inhalant type medications like albuterol and stuff?
That's definitely something that we should think about. It isn't in this design for the PDR, but I think that's a good thing to think about. Can you make sure that that comment goes in the Slack channel so that we don't lose it?
Will do.
Can I make a really quick admin suggestion? Can you add slide numbers to these slides really quickly so that when we make comments, we can reference them back to the slide number?
That'd be great. You're asking for slide numbers on the slides? Yeah.
Is it something you just turn on in Google Slides?
If anyone knows how to do that right now, let me know. But I think that in the interest of time, I don't know that we're going to be able to put that on right now.
My bad.
Yeah, it'll be on. I just tried to apply it.
Oh, awesome! Thank you, Ethan.
Did that work?
Fantastic. Great.
Did it work? Yeah.
Yeah, it worked. Awesome. Thank you. Okay, so as we mentioned before, we've got essentially two electronic controllers on this design, which handle different parts of the operation of the ventilator. And the reason for splitting them up is that they operate on different time scales. So the cycle controller will control things that are happening immediately in the ventilator, and the UI computer will handle more complex tasks that involve interaction with the user. And the reason, the concept behind splitting these up is that we want one computer to operate in a very predictable manner. So this is something that should operate, go through a cycle in a very deterministic time, right? Every 1/50th or every 1/100th of a second, it does a very specific number of things, which means also that it can't be too complicated. And so for things where we have to detect user input, where we have to display things, where we essentially have an operating system running in the background, it's harder to make things operate in on a predictable cycle like that. And so the idea behind splitting these two controllers up is so that one of them can be as simple as possible and the other one can handle the more complicated tasks. And so in general, I've just listed out the tasks for each of the computers. The display and user interface computer, one will keep an eye on the cycle controller and raise an alarm if the cycle controller stops responding. It will handle the user parameter setting, the ventilation mode setting. It will report the sensor data, typically in graphs. And that's the respiratory cycle plot display. And it will also handle the tidal volume-based parameter adjustment. Now, this is something that we're still kind of working on, but the thing about tidal volume is that this is not something that operates on a 1/100th or 1/10 of a second time scale. You actually have to observe several breaths of the patient to determine the tidal volume. So this one requires some memory and storage of those parameters. Now, the nice thing about tidal volume is that it's not something that you have to respond to right away. So the machine has a minute or two to make a decision and to change this. If it doesn't immediately command the tidal volume on every cycle, the cycle controller will simply continue the breathing of the patient unobstructed. The user interface computer will also display detailed alarms. So more than just creating a beep or flashing a light, we want to be able to have the specific information to the user about what the machine is trying to alert about. And then it will also sound the alarm specific alert. So in hospitals, you typically have a few different sounds which mean different things. And so to have recorded sounds that play back, we need memory and we need something a little more complicated. So that happens on the user interface computer. Down on the cycle controller, the tasks include watching the UI computer. So it's a mirror of this other task, watching the UI computer and sounding an alarm if it stops responding. The closed loop control of the blower and solenoid. So that's the immediate real-time control loop for those components. It will control the respiratory cycle. So the breathe in and the breathe out, the timing of this, the control of the components, that's handled by the cycle controller, and it's designed to be completely autonomous. So if it stops receiving information from the display computer, the cycle controller should continue operating. It just won't be receiving the changes to those parameters, but the loop will continue to run. This is that timing control, the continuous mandatory breathing, continuous mandatory ventilation. Timing control, that's if the patient doesn't breathe on their own, there's a minimum amount of breathing that the machine will do, and that's handled here on the cycle controller. The sensor data reading and sensor failure alarm, so this is the real-time monitoring of the sensors. The overpressure, respiration, and broken loop alarm, we all expect that to happen on the cycle controller. And each of these controllers will have their own ability to raise alarms, flash lights, or make sounds. But the more complicated information alerts will have to happen on the user interface computer. And at the very basic level, if either of these fails, we want the other computer to be able to raise an alarm so that an intervention can be taken. One important thing to note here is that this design is not fully redundant. So if any of these items fail, an immediate intervention will be needed to keep the patient alive. What we are trying to do in this design is to design the system such that if any of these fail, A, an alarm is made so that attention can be given to the system, and B, to design the system such that you don't immediately kill the patient. If something fails, you have some minutes to make an intervention where the patient can still be saved. And that's sort of the failure concept of operations here. It would be possible. Yes.
Ben Lamond here. Real quick, one idea for that might be to keep a designated pin in hardware for each of those boards set and always defaulted to high, basically as a redundant default failed state. So every time that thing gets turned on, it's in a failed state. So no matter what, that thing can't start working inadvertently and sending anything to the patient without it being set to true or positive.
Yeah, so what you're describing is essentially a watchdog timer, right?
I'm saying have that pin be default into a failed state in hardware on boot up without even being set by software.
Certainly, and then it needs to be reset every so often. And if you don't receive a reset within a certain time frame, it goes back to failure.
Yes, that's correct.
Yep. Yeah. If you want to put a comment on that in the Slack channel, we can continue that in the Slack. So it would be possible to make a fully redundant system, something that in the event of any failure of one particular piece of hardware, the system will continue to run completely as intended. But this also makes the design a lot more complicated, and it will mean that the ventilator is more expensive, which means we can build fewer of them, and it will take us longer to make a useful ventilator. Something I'll also mention is that most ventilators are not fully fault tolerant. Most medical ventilators in use in hospitals do not have full fault tolerance redundancy.
I have a question about Derek Yerger here. For the controller, is it not possible to have it still do the activities of controlling the electronics and doing some sensing? If there were a failure in the Raspberry Pi, there would be some data collection and reporting back to the user would be gone, but it would still be able to serve in a capacity of making sure the patient is being ventilated.
Yeah, that's exactly what we were talking about in the last slide. So the idea here, sorry if I didn't make that clear, the idea here is the cycle controller is completely autonomous, with the exception of being able to modify these settings and that come down from the user interface computer. So the cycle will continue, but the settings cannot be modified if the user interface computer goes down. Yep. If you have further questions, please put them in the Slack channel so we can discuss them at the end. All right, next slide here we have is our working baseline of the pneumatic design of the ventilator. We have an air intake coming in here, which is pressurized by our CPAP blower here, which is our pressure source. It goes through a mixing chamber where the additional oxygen can be added as well. There's an optional O2 sensor, and we're not sure if we're going to provide that yet. The O2 sensor costs about 1/5 of the entire ventilator parts cost. So that's something that's still being considered. We have flow sensing on the inlet and outlet side, and we take the subtraction of the two of them. We difference these to determine the amount of gas flowing into and out of the patient. There's a humidifier which heats and humidifies the air and is passed to the patient. So patients that are intubated, they don't have the moist sinus of the throat and the trachea, which usually performs this purpose of moistening and heating the air. And so when a patient is intubated, we need to provide that. So we have a water tank with a heater, which humidifies the air. We have a patient filter, then you have the patient limb going out to the patient. This would either be endotracheal tube or a non-invasive mask type, but this goes to the patient's lungs, returns through the expiratory branch through another filter to isolate the patient. So these are bacterial viral filters, going through our outlet flow sensor, through the solenoid valve and out a tuning valve, which is essentially an adjustable orifice, which is set one time at manufacturing and then left in place. And this basically supplies the back pressure, which allows us to control the pressure of the system by varying the speed of the blower. The electrical portion of the design is shown here on this slide. So we have all those components that we just talked about here on in the pneumatic design over here on the left. The sensing, as we mentioned before, comes back through these sensing tubes. So these are essentially just like hoses that bring these pressures back to a set of sensors that are on a custom circuit that we are going to design and build. One thing about this board, the intention of this design is to try and put all of the electronics on one single board. And this does a few things for us. This reduces the complexity of the design so that assembling this, somebody doesn't have to kind of punch different wires to different things. It also improves the signal quality and reduces the risk that we will have electrical interference causing problems between components or noise and things like that. And so what we intend to have is, as much as possible, all the electronic components on one single board, and that includes sockets for the Arduino and the Raspberry Pi, so they can all plug onto the same board with the same ground plane, which helps deal with some of the interference issues. The one exception is the blower driver. So this is a high current device that creates a lot of noise, and we're going to leave that on a separate board that'll be off of the PC board to provide a little bit more isolation to the more sensitive electronics here on the board. The board, we have flow sensors which pass through anti-aliasing filtering, is converted to digital signals by the Arduino, which then processes the control commands going out to the blower and to the, whoops, I missed the solenoid here, but the solenoid, it also controls the solenoid. It will also do some immediate monitoring of the health of the system, as well as communicating this information to the Raspberry Pi. And it also has its own sets of alarms. The Raspberry Pi will handle the display and user interface. And so it has it's a touch screen on the face of the ventilator, which also includes a set of speakers so that it can sound alarms. And it will have also of the flashing lights and the alarms inside of the PC board. The ventilator will be powered from a 12-volt DC power supply, and the reason for this is that 12-volt automotive batteries are widely available around the world, and they can serve as a battery backup so that the system is not immediately dependent on mains power. And one of the reasons for this is that, you know, if you have individual failures, you can have alarm go off, can have someone intervene, but if power goes out in the hospital, you can't have 100 ventilators all failing at the same time and expect your nurses and doctors to be able to take care of all of them at once. And so the machines need to have some kind of a battery backup. And we've also been discussing the possibility of adding an additional small battery on this board to allow the system to sound an alarm if the 12-volt itself is disconnected. But it won't be able to keep the blower or everything else running. A few words here for design for manufacturability. I think manufacturing definitely deserves its own discussion, but just a few words about our intentions here. We want to focus on off-the-shelf parts, things that are easily available and have solid supply chains. So anything that's very custom or things that are sort of unique scientific lab-grade components, we want to avoid. We want to limit custom or 3D printed parts. And if possible, whenever we do have parts that need to be custom made, we want them to be able to be built by volume processes such as injection molding or laser cutting. We also want the design to be hand assembled. We certainly don't want to make it in a way that can't be assembled with robotics or special machinery. But in a lot of places where this stuff isn't available, we want the components to be assemblable by hand. And finally, the circuit board as well is designed to be assembled by hand, you know, with a skilled technician and a soldering iron, but also to be built such that if you do have a robotic assembly line available, you can also build it that way. The listing there, we have an interface control document, and so this is essentially a document that keeps track of all of our sensors and all of our signals so that software and hardware are on the same page about what's coming in and out of the components. Each of the signals has a name. It has a source and a destination of the input or an output, and I guess this is defined from the electronics perspective, and the type and range and connection, the pin connection of each of them. So this is just a screenshot cut out from the actual document. So the actual document has quite a few more entries and is the controlling document for it. So, you know, don't take anything from this slide here, but go to the link to get information. So let's talk about what some of these signals look like, what we expect to see from these signals. So this is taken out of a textbook. This is an idealized ventilator waveform for a patient. So what you see is one inhalation, exhalation cycle. The pressure supplied by the ventilator peaks and then goes to a plateau during inhalation and then drops off during exhalation. And important thing, this diagram shows that peak, that positive end expiratory pressure, and that's a specific feature of treatment for ARDS in that we want to keep even during exhale, a small positive pressure to keep the alveoli from closing back up. With ARDS, with damaged lung tissue, their lung tissue doesn't produce the surfactants that healthy lung tissue produce, which keeps the alveoli from sticking together when you exhale. And if you don't have this, it can be dangerous to let the pressure go zero. And so that's why we see this whole plot is shifted up by the PEEP. Flow, you see during inhale, you have the flow increases and then decreases again when you get to plateau, and is essentially zero during plateau. And then when you exhale, you have a negative flow out of the patient, which then decays again back to zero as the pressure equalizes with the ventilator and the lungs. The volume, you see the same thing here. The volume is essentially the integral of the flow, and the patient inhales, or the ventilator blows air into the patient's lungs, increasing the pressure, increasing the volume, and then it's stable, it's constant during plateau, and then during exhale, you see it fall. So what does this look like in the real world? These are recorded waveforms from the actual sensors in the prototype right now. So we'll see, we have our command, which is what we mentioned before. This is the profile that is being commanded by the cycle controller. And the pressure delivered by the blower follows. We have the inlet and outlet sensors for flow. And so you can see here during inhale, the inhalation flow is greater than the exhalation flow. And they're essentially the same, equal at plateau. And then when the pressure is dropped by the ventilator, allowing the air to flow out of the patient's lungs, you see the exhalation branch being higher than the inhalation branch flow. If you take the difference of these, you subtract them, you see that same thing here. You have an inspiratory flow here, a plateau, and then a negative flow in exhalation. And if you integrate this, you get this same sort of shape. You get the inhalation, the plateau, and the exhalation. So right now, our biggest challenge and one of our biggest open items is flow sensing. It's hard to get reliable data that shows this sort of behavior at a wide range of pressures and flows. So different settings on the ventilator and different regimes of operation can produce different results, in addition to being very noisy as well. So I'm going to turn it over to Ethan for a bit to talk about our current flow sensing problem, because this deserves a little bit more attention, because it's our what I would consider our biggest open item. So Ethan, you want to take that away?
Yeah, and I think there's already a flow sensing channel. I think a couple of people in here have participated in that. There's some historical data. If you guys join that, it's hashtag flow sensing. And then as well, this is going to become a larger focus area for us, trying to nail down a strategy here. But in general, tidal volume is required to ensure adequate patient ventilation. So if you just go with a pressure cycle device, it's very easy to underventilate, and it's as well pretty easy to overventilate. So if you're not getting that feedback to the machine, I think that's to the point where we're not kind of meeting our minimum viable product. So, but it's also complicated by the fact that because the patient can breathe spontaneously, we don't think we can just measure delivered volume. And so we really need both that inhale and exhale to be tracking for double breaths. And, if the patient spontaneously tries to breathe during an exhale cycle, they're not really going to exhale, and then that next breath is going to come in. And so being able to prevent that requires measuring the volume flow in inhale and exhale. I'm going to start, so this is just kind of as a thing we kicked off with in the last day, that this is going to become a larger focus area. So I'm going to type up a better specification that we can start sharing on what we need to accomplish. But just at a high level, we're looking between a flow rate of 0 or maybe as a sensitivity around 0.5 liters per minute would work, depending on what logic we can write in there, and then up to 80 liters a minute for peak expiratory flow. And again, missing those edges could be okay. It decreases your accuracy, but obviously we don't want to do that. But if it totally simplifies the system to have a slightly less accurate volume integration, the volume is not a hard number. It's going to be patient lung dependent, and so if you're 5 milliliters over, you should be okay as long as you're monitoring other parameters, or if you're indicating 5 milliliters over. And then, as Edwin was talking, the flow integration leads to tidal volume, and so we need to track kind of numerical error and linearity of response as well if we're doing integration.
Hey,
Next
Ethan,
slide.
just let me know if you, I'll advance slides for you.
Next slide. Slide. Click.
There you are.
Click. Great. So I'm just going to talk through 5 different sensing types that we've researched or implemented at some level, just to give everyone background on what we've tried and what issues we've had with it, and maybe where we think we're going to go next, but open to thoughts and discussion in the hardware PDR as well. So the current baseline is a Newman tachograph. I think the simplest picture for me is this one in the bottom right. It's basically similar to an orificing flow sensor, but without trying to catch that venturi. And so it's a differential pressure sensor based on a flow loss. And so that's what's shown in the picture here. The issue that we had with that so far was really noise, I think. And so, that's kind of the baseline strategy, I would say, but it may be worth exploring other construction and manufacturing options. I think the only one we've tried is a single 3D printed part. So there's definitely some room to improve there, but this is the typical design for spirometers, which are used to measure lung health and things like that in patients. And so, it's used in this kind of flow regime as like a confidence check. And so this bottom left picture is a medical spirometer. So, there's some confidence there that it's in our ballpark. So next slide. The other thing we tried is a venturi flow meter. I didn't have the picture. We've also implemented this. The big issue we had here is the way that the differential pressure is calculated involves taking a static reference and a low pressure reference and a contraction. The problem with this is it's a nonlinear response, and so sizing it to have an adequate pressure drop for the high flow rates up to 40 or 50 liters a minute means that we actually have a pretty low response down in the 0 to 10 range. And then as well, this isn't an issue as much in the current prototype, but it's not bidirectional, which was more of an issue before. So it's mainly that nonlinearity of scaling. And basically the first time we implemented this, the flow rates on exhale tend to be lower than the flow rates on inhale. And so we were kind of systematically underestimating the exhale flow. And that again is something that's probably addressable with a little bit more design effort, maybe differently sized. So those were like similarly sized venturis. And then just in the bottom left is a picture of a gardening venturi that we'd used on a different project, which is, at least to a first order, is sized almost exactly right for what we're trying to do here. So we have used a 3D printed part, but the nice thing is these are kind of cheap injection molded $4 parts if that ended up being the right sizing. Next slide. So then the next thing that we looked at is a hot wire or thermal anemometer, and these operate by a few principles, either constant temperature or constant power. But this is similar to what's in the airflow sensor of your car. And as the flow goes past the heater, you're either measuring the power and temperature of that heater, or you're measuring the temperature downstream, and you can see a time response. There's a couple different ways these work. You can either see a time response to that temperature sensor based on the heat input, or track the heater power or temperature to try and correlate that with the heat transfer coefficient and flow. What's shown in the bottom left is at least the first pass implementation that we haven't yet implemented, but the way the PB560, which is a Medtronic open source ventilator, does that flow sensing is a similar way. They have a small restriction in the main channel and then a bypass flow that goes to a much more sensitive linear thermal mass flow sensor. And so they're, it's a highly calibrated sensor. So the housing needs to as well be, calibrated individually. So this is just my thought on how to implement that here, but we can keep playing with that. I think Edwin has a few of those prototype parts coming soon. And then the next slide. So then the last that we haven't really looked at in this project, but we have used a fair bit before kind of in our other engineering projects, is a pitot sensor and constrained flow. They tend to, at least I haven't actually done a mathematical comparison of all of the different options here, but have pretty small signals in general for the flow rates we're talking about, and kind of have a more involved construction design, trying to get that measurement without wall effects and things like that in the flow. But if you look in the flow measurement channel, I did just find like a patient side pitot monitoring system for flow in a ventilator. So it's at least an option that has been used before for ventilators. So that's kind of the current state of the art. I know, Edwin, you spent a lot of time on this too. Is there anything I missed in terms of catching everyone up to state of the art?
No, I think that's good, and it's important that we go over this because this is essentially our main blocker right now for moving forward with from prototype to pre-production. Yeah.
I have a question.
Yeah.
Have you looked at sonic anemometers?
That would be a good thing to bring up in detail in the flow measurement channel. So if you want to hop on over and invite yourself to flow measurement, there'll be discussion of flow measurement stuff there.
Yeah, that's pretty much all for me. I mean, I'll just briefly answer Derek's question that we haven't looked at ultrasonic flow meters or other kind of sonic flow meters based on my experience that they're like a little pricey, but I haven't looked again in this regime. And if that's really what we need, then that's what we need. So I think it's worth exploring for sure.
Excellent. Thanks, folks. A few more slides here, just wrapping up more of our design control documents. So another important document is a failure modes effects analysis. And this is something that that's a very useful tool for determining, for making sure that we're hitting the right risk items. So the basic mechanics of a failure mode effects analysis is this simple equation here, which is that the likelihood times the severity is the risk priority. So you can see this in the screenshot example at the bottom here. Again, the real document is up here, so if you want to reference anything, definitely go look at that document. But essentially, for each possible thing that can fail, we determine a severity, so how quickly this causes a problem for the patient, and the likelihood of occurrence, how likely this would happen. And then if you multiply these together, what you have is a risk priority number, RPN. And this basically allows us to see if we have one particular risk that is much higher than the rest, right? If you design something that is safe in situations 1, 2, and 3, and then situation 4 is really, really dangerous, then it's still just as dangerous as situation 4, right? So it's sort of this, like the chain is only strong as its weakest link. And this is the tool that we use to systematically go through all our failure modes. So this is a very useful tool. And then what we use is here in the second half of the FMEA is the corrective actions. And so based on these risk priorities and these factors, we determine what we can do to make the system safer or operation safer. So for example, we could add a sensor or add a check to the software, or it could also be an operational thing where if we instruct the user to set it up this particular way or to use it this particular way, it will reduce the risk or the severity of one of these factors. So this is an important thing. Here I've listed out a few of the open items that we're still tracking in the design that we're still trying to resolve. We've talked about flow sensing already. We're also in the process of developing our software requirements and how they interact with our hardware requirements. Obviously, as hardware requirements change, and for example, like the type or the level of noise we have in our sensors will affect what the software needs to do. So we're keeping close eye on that. Something we still need to consider is also the oxygen compatibility of our electrical parts. The nice thing about this system is that there's essentially only 2 moving parts in it. It's the blower and the solenoid, but seeing as we'll be using enriched oxygen flow, we need to make sure that we've taken that into account. In manufacturability, we need to scrub for supply chain issues. We don't want to pick parts that there may only be 20 of in the world or are hard to source or hard to build. The mixing volume and how we bring oxygen is also still in design process, and figuring out what level of battery backup we need for the alarms is still an open question. And again, the failure mode effects analysis is not a good way to judge that.
Hey, Edwin, just
yes.
brief introduction, and I had put this as a comment in the slides, and maybe it's something for Daniel to answer. As people identify risks that aren't captured in the existing FMEA, as we go more detailed in the design, I think we should have kind of a risk review at some point. But in the interim, as people think of risk, what's the process for making sure that those are captured in the FMEA?
Yeah, so you can put it in the risk quality if you identify one, or engineering. I'll keep up with both of those. The FMEA we can use for development, but that's not actually compliant with the standard we have to use for medical devices. So I'm actually translating all that into a 14971 risk document. So if you have something that's like specific to the design, like a failure mode, yeah, just send that out or make a comment in the current FMEA. If you identify something like an overall hazard with the device, like, you know, it could harbor some infection or something like that, that isn't necessarily a design failure mode, let me know and I'll add that to the overall risk assessment of the device.
Yeah, thank you, Daniel. So a few things that are going to be coming up next. We have that failure modes effects analysis. So that's something that's ongoing. Once we have some of our hardware design issues sorted out, we'll be building the pre-production prototype. So that's something that looks a lot more like that 3D rendering and less like a kitchen table build. And once we have that built, the next major milestone is the critical design review. So this is sort of like the big brother to the preliminary design review. And this is where we've actually built the prototype. We've actually tested it as a fully built prototype. We've collected data on it, and we'll be going through and stepping through step by step through each of the hardware requirements and demonstrating through the data that we have met them. And this is really, that will be the gate to manufacturing. So once we've passed, we should do the CDR when we're almost ready for manufacturing. We want to prove to ourselves that we have built the thing that we intended to build and that it's going to work on a patient and be effective. Yep, and so we have about 15 minutes left in the meeting, and so I'm going to take it on over to, I'm going to stop sharing my screen here. We'll take it on over to the Slack channel and see if we can we'll address as many of the questions as we can now, and then continue the conversation in the hardware PDR Slack channel. So I'm just going to scroll up to the top and see.
Can you share your screen so that we can all see?
Yeah, certainly. Let's go ahead and do that. Here, so you should now be looking at the hardware PDR Slack channel. Okay, so I think how is this different from a bridge ventilator? I think we've answered that, right? Yeah, and it's a good question from James there. It's the question of what is the population we're trying to serve, and like how many people are going to be on the just barely needing a ventilator side, and how many people are going to need a ventilator for 4 weeks to get back to health. And what we found from talking to a lot of our doctors is if you go on a CPAP or sort of a lesser intervention, you almost always end up needing the full ventilation eventually. Okay, so James asks, why in RPi and Arduino wouldn't the supply chain be simpler with one type of compute? And I think we've answered some of that already in the presentation. The separation of essentially a fixed state machine with very predictable operation and something that can handle more complex things like displaying graphics.
Hey, Edwin, I just want to raise that I think this is something that, a lot of people have flagged, and, I don't know if we want to do a separate, discussion just on that. I think your logic is sound. I just want to make sure that as there have been a lot of opinions on this and concerns raised even from the beginning about the strategy, we should make sure that we're, not kind of biased on our past decisions.
Certainly, we'll continue that discussion in the hardware PDR channel. Okay, from Kathy, possibly need a provision for adding inhaled medications. Yep, we mentioned that, so we'll try to keep an eye on that and have that as, because that's definitely something that most ventilators provide. Neil says on slide 8, add independent hardware watchdog for each compute element. Perhaps the watchdogs can watch each other as well. So it's definitely possible to get just like a single chip, and that chip itself is a completely self-contained watchdog machine, which will raise an alarm if it doesn't receive a reset signal. So it's basically a countdown timer. And if you don't reset that timer every X number of milliseconds, it will raise an alarm. So it's easy enough to just put one of these chips on each of the compute units instead of having the compute units watch each other. Ralph asks, how are we planning to prioritize controller alarms versus UI computer alarms? And the answer is both of them have to essentially be autonomous because we can't assume that the other one is working. So if one of them fails, you raise an alarm. And what we sort of the concept right now is that because the controller alarm it can be much less specific, right? It can be for or it can make us turn on a light, but it can't actually tell you what's wrong. So what we want is to have that raise an alarm to the UI computer, which should respond with an ACK. And if it doesn't respond with an ACK, the controller will then sound its own low-level alarm. But if it does, if the UI computer does ACK, then it will sound a more specific alarm and display something on the screen describing what the failure mode is. And from Joseph, if the Raspberry Pi or similar is going to be storing data long-term, that means writing to the file system. The file system must be carefully selected to ensure that it does not lead to file system corruption, which is a widely reported issue with the stock Raspberry Pi configuration. Yes, that is correct. So we either need to find a way to make sure that it always is closing its file interactions, or to have some sort of graceful shutdown. If it, powering down a computer with a file system just abruptly often doesn't work. So that's a good point. That's something we need to look at. Yep.
Hey, Edwin, something Kyle brought up, which I think is like a big, I raised it in the last meeting, but it's a big topic that I think is kind of worth the broad awareness. I just kind of wanted to step in with it, is that the kind of the controller logic that we've been talking about, what's running on the Arduino notionally by that logic breakdown, is actually pretty immature. I think as the hardware has developed, as we've been learning more about the medical requirements, we really don't have a good, and if someone feels they do, then definitely correct me if I'm wrong. That's why we've been reaching out to a lot of controls experts, is to understand exactly what kind of controller laws we need, what kind of state machine logic we need. That's something that was a bigger gap that we identified later on than I think we all would have liked. So that's something that, obviously should be done first, and we need to make that a pretty high priority going forward. So we're working on that and trying to do as much in parallel as we can without that. But obviously that raises, and kind of the high level, I say a lot of times we do our engineering design, we're trying to do a 12 to 18 month program in a number of weeks, which means doing a lot of stuff in parallel that you shouldn't, which means we need to be careful, be communicative, and be willing to revise stuff if we find out that we were wrong. So that's the only way we're going to hit our schedule, but that's also, obviously a risk that we're taking on. So, but not to bury that in the opening, I don't really think, other than the one paper on controller logic and ventilators and the people we've reached out to in the last few days, we have a handle on that, actual controller structure, the state machine that we, really need for the final build. I don't know, Edwin, do you feel that's accurate?
Yeah, I think that's true. The software that I have currently running on the prototype is just to test the hardware. It's not meant to be a ventilator. It's meant to demonstrate that the hardware works and to collect data that can then be used to develop those control laws. Yep, thanks for that. Jam writes, clarification about modes. I believe 2 modes are pressure assist and PRVC, and we should pick a manufacturer and stick a naming convention to minimize confusion for clinicians. Yep, that's a very good point, and Jam has added this table here, so have a look at that. Joseph True writes, if the Raspberry Pi or similar is going to be storing late, okay, this is the same comment that we had earlier. Yep, exactly, we need to be worried about file system corruption. Cal writes about the Arduino being referred to as a real-time controller, related to James's question about the split RPi Arduino situation. It seems that the current thoughts were that the Arduino was simpler and better for controlling things in real time. Real time needs to be carefully discussed and defined because there is no such thing as true real time in a microcontroller. This may require putting RTOS on the Arduino to meet actual timing requirements. And Arduino is not made for life-saving applications by default. If this is needed, then the split RPi Arduino situation may need to be reevaluated. Why not just have an RTOS on the RPi and no Arduino? So this looks like there's plenty of discussion on that. So thanks for jumping in on that, everyone, and we'll continue that discussion in the channel here. Ralph says, if we are setting the temperature via hot water humidifier, does that mean we have to take it as an input from the medical professional? I'm not sure about that, and so that's something that we should look at, but we do need to have some feedback on that so that if it runs dry, it doesn't overheat. Yep, label the water heater humidifier. Yep, we'll do that. Thanks, Martin. James writes, is it a single seal one-way valve between the O2 and the motor blower? Want to watch for fire concerns in a weird failure mode. That will generally be, we don't exactly know what that interface is going to look like. In a lot of medical situations, you have a constant flow regulator that's on oxygen tank or oxygen source. And so that will be providing a pressure that is always positive and always higher than the pressure that we have in our ventilators.
Edwin, I think what he's talking about is, if there's a fire risk from oxygen entering the blower and we have the oxygen entering downstreams and there's some kind of blockage, then there's that one-way valve between the blower. So right now it's it's notionally, I think we actually haven't identified a part, and it's something that is high on the list, but along with everything else, a CPR mask valve kind of thing, the one-way little, silicone flapper things, to just kind of keep any substantial oxygen concentration from going upstream into the blower. Yeah, that's sort of the current baseline, but that's definitely something that someone could take on and nail down. Yep.
Yeah, and we have a physical model that was generously provided by Modelon in their compute. They've volunteered their computing software and generated a physical model for us so that we can model these kind of things. Also, one thing I forgot to mention earlier about the controller setup, the Arduino is just there because it's what we had on hand, and it really is just representing hardware. We don't need to use Arduino as a platform. At the end of the day, it's a Atmega microcontroller with supporting electronics, and essentially what we need is some kind of controller with supporting electronics. So that is up for discussion. And this is what Joseph writes right here: is Arduino is really an Atmel MCU with a few extras. By putting it directly on the PCB, we'll save off a chunk of cost and improve reliability. Yeah, I agree with that. On the other hand, it does add extra risk by adding complexity to the board. If we do have a controller on a module, then we know that it works and we just plug it in. If we design it on the board, there is a risk that we'll design it wrong and something won't work. And for that reason, I suggest that we keep the board as simple as possible and try to incorporate as few new things as possible, but that's up for discussion. Daniel writes, how do we account for leakage in the flow measurement for the tidal volume? How many cycles before we get an accurate measurement, and what do we start up with? I see a risk that we don't provide enough volume when the nominal pressure of the lungs are altered by pathology. Yep, that's a really good point. And there will always be some leakage in the system, and what we will need to do is to do a normalization of the flow measurement. So there's you can look at the flow measurement as a sort of chart that goes up and down, but there's another way to look at a flow measurement where it's a closed loop, where if you have pressure on one axis and flow on the other, I believe is correct. You'll see the thing actually come to a loop, and if you normalize your measurement such that the loop closes, basically it returns to the same value every time. You can account for some constant leakage. We're assuming that on a cycle by cycle basis, the lung capacity of the patient can only change so fast, like with the number of breaths. But that's definitely something that we still need to think about. So thanks for that. We do definitely want it to be able to track the physiology of the patient as it progresses. Slide 10, are these PCBAs going to be surface mount or through hole? Yes, through hole, there will probably be a few through hole components for connectors and such, but the board will largely be manufactured with hand solderable SMD pads. The reason for this is SMD parts are much more easily available, and if you design the circuit board right, they can still be assembled by a reasonably skilled technician with a soldering iron. Justin says, mentioned in previous meeting, but want to record it here. The exhaled air air may have more humidity than the inhaled air, and therefore the pressure difference measurement might not let you natively calculate tidal volume. That's definitely a concern. We have seen a number of other ventilators have this design where they difference the inhale and exhale flow, and they have a way to calculate it. So there's probably some normalization that needs to happen there. Daniel says, for the power supply, we should try to get a 6061 specified part to help with risk compliance. Got it, thank you. Martin says, while the humidified is off board, the heater switch is on the board. No noise issues here. Yeah, we'll have to provide some filtering and protection for that. We're still trying to figure out exactly where the humidifier is going to go. It's full of water, and we have a bunch of electronics, and it still needs to be accessible by the clinicians. So there's something that needs to happen there. James says, is a 12-volt battery connected to a monitor charging system? Yes, so the plan is to have it connected to mains power so that it is continuously being charged, essentially acting as a uninterruptible power supply. And to the question of, is it assumed to be known good? The nice thing about a car battery is even a poorly working car battery will have quite a bit of capacity, and a fully working car battery will give you something like 20 hours of operation with the current design. And even a poorly working car battery will give you a few hours of operation, and we'll also add, there will be voltage monitoring on the ventilator to alert to problems with the battery. Yep, Daniel just writes back, we should have a monitor circuit, which is, it's there in the circuit diagram if you see that in the slides. Ben says, what is the theory behind having the Arduino controller continue despite failed communication on the Raspberry Pi? I get throwing the error and flagging an alarm. Is it inherently safe to continue to perform the medical functions if you're not capable of receiving information from the interface controller? That is the design intention. The interface controller is needed to change the parameters, and if you lose the ability to change the parameters from the computer, you will sound an alarm, so it can be reset. But what we expect is for the cycle controller to continue operating with the previously set, with the parameters, the breathing parameters that were previously set by the doctor. Ralph asks, when you say the PCB is hand assembled, do you mean that each unit sensors, wire, etc. will be hand soldered? If so, how do we want to quality control that? That is a good question. We should use regular visual assembly quality procedures. It's really designed such that we could build this at a, where the resources are available. We'll want to build this at a board house with a pick and place and optical inspection techniques. But if that isn't possible, we still want it to be designed such that it could be built basically by hand. Add a solenoid on slide 10. Thank you, Neil. Slides for review. Thank you. Let's pin that to the channel. There we go. Thank you, Curtis. Sample fuse. Thanks for the fuse. Ralph says, are we doing this integration of flow rate on the microcontroller of the Raspberry Pi? That's something that it's part of the discussion of what controller we use, because if we use the Arduino, there isn't enough memory to do that. So the integration of flow rate would have to happen on the Pi. But if we build something with more memory, we could possibly do it on the controller, the cycle controller as well. Can we get a basic electrical only schematic for the existing prototype? Yep, certainly. So that I'll be designing the PCB, or me and several others will be designing the PCB in this coming week, and then there'll be a prototype for that. In the meantime, I'll add part numbers to the interface control document so you know what you are talking to. So go have a look. I'll come back and add a link to that document as a comment to this message here on this thread. Joseph says, I've worked a bit with the MAP style sensor, requires calibration. Yep, that's good to have some experience on that. Recommend having electrical schematics done or started before you do your prototype build. Yep, that's the priority for the next week, to design the circuit board and have an electrical schematic. State machine, that's probably a good question for the software team. So the software team has been doing a lot of work on the architecture of the software. So go introduce yourself if you haven't already on the software channel, and they should get you up to speed. Is there a need to harvest data from the device? So that's open question. We definitely need to have patient history on the screen, but if we need to provide like a report, I think that's something we need to think about. Adding audible visual alarm to the Arduino, I think we addressed that in the channel. We're running a bit over time here, so I'm going to try to hit as many of the questions as we can, then we'll continue. I'm going to finish with the questions that are on screen right now, and then we'll continue in the PDR, hardware PDR channel here on Slack. On the subject of alarms, how loud do they have to be? Looks like we got a lot of answers on this already, but JAM found specifications for medical devices and the how loud they have to be. It'll be on there. Joseph says we should identify appropriate board sizing and establish at least preliminary standardized mechanical mounting holes. Absolutely, yeah. So this is all going to be defined in the PC board. Derek says for RTOS, a low-cost solution would be Zephyr OS on a commodity SoC as a single CPU solution, but moving from an accessible platform such as Arduino increases complexity of the project and creates a single point of failure when the four life-saving aspects are consolidated to the Arduino and UI elements on a separate device. In either case, manufacturers disclaim their MCU SoCs are not to be used in medical life-saving devices, which may not matter for the target market and circumstances. Derek, thanks for that. I think that's a pretty good summary of the situation at hand. And then David says, just making sure, suggest include design for test board review and reviewability to use quick mount and low-tech field test jigs. Yep, you got it. That's all going to be in the PCB review, which hopefully will be coming next week. Okay, we're about 10 minutes over time here, so I want to let people go. Thank you very much for devoting your time on a Saturday and on all of your time to work on this. This is essentially a volunteer project, and so I'm very grateful to everyone for throwing their weight behind this for something that's clearly very important. So
essentially volunteer, Edwin, or do you know something I don't?
No, everyone's volunteer. I don't think anyone's gotten as much as a granola bar out of this.
Well, thank you.
I'll mail you some granola bars.
All right, thank you, everyone.
I'm still waiting on my first granola bar paycheck, man. Is it coming or what?
Yeah, well,
everyone's got to take a number, all right?
Exactly, right? They'll tax it out of you. You'll get 2/3 of a granola bar. Continue the conversation on the Slack channel, and we will continue. Hi there, Derek's cat. We'll continue the design effort. Thank you so much, everyone. Have a good day.
Thank you for the